Swayam Prabha. Digital India. Educated India.
Hi, I am Ganesh Malayat. I am a research scholar in IIT Kharagpur under Professor Ajay Sidpara, and I am working in fabrication of micro tools using micro EDM. Welcome to the lecture on Introduction to Mechanical Micromachining. In the last classes, you have studied different kinds of manufacturing processes, machining strategies and all. In this lecture, you will be studying how to fabricate an end mill cutting tool, that is in micro dimensions. So, what is a popular tool fabrication process in the macro region? Actually, it is called grinding, tool grinding. The tool grinding process is not much reliable in the case of micro machining of cutting tools. Why is that? The tool grinding process is a contact type process. So, there will be always cutting contact between the tool and the workpiece. So, while dealing with very small cutting tools in the micro dimensions, if there is high cutting force or the contact force on the cutting tool, there will be, or on the workpiece, there will be chance of breakage. So, that is not easy to make cutting tools using grinding. So, we need a process which is not contact, like in non-contact type, which is capable of machining the cutting tools. There are different processes like that. One example is laser, other example is FIB, that focused ion beam machining, and the popular example for non-contact type machining process is electrode discharge machining or EDM. So, in this lecture, we will be demonstrating how to machine a micro end mill tool using EDM, that is micro EDM. Okay. And why we are using micro EDM, or what is the specialty of an EDM process? So for that I will explain shortly like how a EDM process works. So there will be a tool electrode, there will be a workpiece. In this case, this is our end mill tool blank. Okay. So what happens, the two electrodes must be electrically conductive, and this will be connected to a DC power supply. One will be connected to the positive terminal and one will be connected to the negative terminal, and there will be dielectric fluid. In this case, it is called EDM3 oil, and there will be dielectric supply in between the tool and the workpiece. And the DC power supply, as the voltage increases, there will be a critical voltage above which there will be dielectric breakdown, and the electron starts to flow through from the cathode to anode continuously. That flow of electrons we will see as a discharge, and this discharge is actually capable of melting and vaporizing material from the workpiece. Okay. So this discharges, so what is the advantage? We can machine any type of material, any hard material which are electrically conductive. Okay. So this discharges, we are trying to make use of these discharges to make micro end mill tools. Okay. So this is in this class we will be demonstrating how to make use of the discharges to make micro end mill tools. So what is our strategy here today? Like, we will be first designing a micro end mill tool and fabricating the micro end mill tool using EDM. To fabricate the micro end mill tool, we must know what is the capability of the machine tool we have. So first is the design of end mill tool. So for that we will be make use of a modeling software, in this case SolidWorks. So this is actually a 200 micron micro end mill tool, in which this is two fluted micro and mill tool. So you can see these two flutes are available. So comparing to the micro end mill tools or end mill tools with a complex shape, in this case the shape is much simpler. So but it's effective because like making a very complex flutes on a micro dimension is very difficult. So in this case what we are doing is we are making a micro end mill tool which is simple in shape but it's effective. Okay. So this is a 2 flute micro end mill tool with of 200 micron diameter. So we have designed this previously and find out what must be the dimension. This has a 200 micron diameter and 0.5 mm, that is 500 micron length. Okay, so we have done the designing part and we found out what is the position of the flank, what must be the dimensions of the flank and all. So after designing, we must know how we can make the design on the workpiece blank. So for that we must know what is the capability of the machine tool we have. We have here a machine tool. It's supplied by Micro Tools, and this is Micro Tools DT110 hybrid micro EDM machine. Okay. So what is the capability of this machine? This is maximum, it has maximum travel of 200 mm in X, Y, Z. Y it's 100 mm and Z is 100 mm. So very small dimensions, but it's enough for a micro EDM machining. Position accuracy is plus or minus 1 micron per 100 mm. Position feedback system, why we must need a position feedback system for a, as explained in the previous classes, we must need a position feedback system while we are dealing with very micron dimensions, because we don't know, like in 1 micron is a or 10 micron is a very big dimension in case of a micro machining system. The slide straightness plus or minus 2 micron per 100 mm over the like plus or minus 0.5 micron over any 25 mm of travel. Okay. And what are the machining, what are the parts of the machine? We have spindle, this which we are will be connecting the tool electrode or and work table in which we will be setting our work. Power supply, a DC power supply, like that's a pulsed power supply, and dielectric supply, that dielectric fluid I told you before, that's EDM 3 oil we are using, and access control systems. Okay. These are the main parts of the machine tool. Okay. And as I told you before, the EDM, the process of EDM is actually a non-contact process. The discharge is responsible for the material removal. Okay. So what is the machining parameters here? The machining parameters are, one is voltage, and that the in our machine tool the range is from 80 to 130 volt. Next is capacitance. This is an RC pulse supply, so that the main thing we will be varying here is voltage and capacitance. So the voltage is 80 to 130 volt. Capacitance we can change from 10 picofarad to 400 nanofarad, and we can change spindle speed, and we can define the feed rate. And two polarities we can set, as I told you, like the tool and workpiece will be connected to the DC power supply. Either it can be the tool can be positively, workpiece can be positive, or the tool can be positive. That's a positive polarity or negative polarity. So what happens as we increases the voltage and capacitance? That's what happens if we change the parameters, machining parameters. So if we are increasing the voltage and capacitance, what happens is, we will demonstrate it later, and I am telling you what happening is the discharge energy, the total discharge energy will be increasing. So as the discharge energy increases, the more material will be carved out from the workpiece, so that the crater size will be increasing. As the crater size increases or the more material is removing, the MRR will be increasing, but that will be affecting the surface quality. So the surface quality will be diminishing, or surface roughness will be increasing. So That's how the machining parameters will affect the whole machining outputs. Okay. So finally, we know what is the machine tool we are using. We know what are the machining parameters we have, and finally we are defining what will be our strategy for fabrication, the fabrication of the micro tool. Okay. So the tool fabrication strategy starting with a blank, we are reducing the diameter of the blank from 0.5 mm to 0.2 mm using a process called electrode discharge grinding. Electrode discharge grinding is very much similar to EDM. So only the thing is, like, we have a block, we have a tungsten carbide block, and the tool material is also tungsten carbide, and we will be doing a operation in which like the standard piece we will be moving with touching the along with the tungsten carbide block. In that time, the diameter of the 0.5 mm tungsten carbide rod will be reducing it to 0.2 mm. That's a electrode discharge grinding process. Here you can see this is tungsten carbide block. The black one is the tungsten carbide block, and this is the tool which we are using, or the blank of the micro end mill tool, and we have reduced the diameter to 0.2 mm from 0.5 mm. Okay. The next process is we want to make the flanks on this tool. So how to make that? We are just plunging the tool down. I mean, we are taking the tool from the spindle and we are keeping on the workpiece, and on the end mill tool blank, we are making two flanks by plunging another tool from the two sides, so that in the finally we will get a micro end mill tool on a base, and there will be two flanks on the two sides of it. So these two sides can be worked as a tool edge or the cutting edge, and while rotating, this cutting edge can remove material and it can perform as a micro end mill tool. So this is the whole strategy of fabrication. So the fabrication strategy start from micro like EDG to reduce the diameter from 0.5 to 0.2 mm, and making two flanks and the two sides of it, so that we will get a two flute end mill, as a simple shape, but two flute micro end mill tool. As the next step, I will be demonstrating the whole process of fabrication of micro end mill tool as we explained here. So for that, I will introduce the user interface to the machine. This is actually the micro tools DT110 hybrid micro EDM. So here you can see there is a panel in which this is just like a CNC machine. The panel, you will be familiar if you know if you are familiar with any kind of a CNC machine. The panel is almost same. There is a MPG mode in which we will be controlling manually, jog mode, and MDI mode in which we will be putting manual data inputs, and auto mode we will be writing program and we will be performing the program. Okay. So the EDM parameters we will control by this panel actually. So what you can see, there is a polarity icon in which we can change the polarity to positive or negative. That means here it shows work positive now. If I am putting, so first for that we have to start the power supply. Now the power is on, and we can change the polarity to tool positive or work positive, so that usually the tool will be connected to the spindle and the workpiece will be kept in the work table. So we can change work positive or tool positive accordingly using this icon. We can change the capacitance from, so it is a coded value from 0 to 6, so that the 10 picofarad to 400 nanofarad we can change So it's from 0 to 6 actually the coded value for that, and we can change the voltage from 80 volt to 130 volt just like sliding this one. And this is all about the setting parameters, machining parameters. So first step will be, we will be finding out what is the optimum parameters for machining, and we will set the parameters. So the first step will be finding out the optimum parameters for machining, and we are setting the machining parameters here in this window. After that, we have to, for the first, as you if you remember, the first step is to reduce the dimension of the blank, EDM tool blank, from 0.5 mm to 0.2 mm, that's 500 micron to 200 micron. So for that we have to find out, like we have to do we have to select a blank micro for micro end mill tool. So starting with, what we are doing here is we are selecting a blank as a commercially available 0.5 mm or 500 micron end mill tool. On the surface of that, what we are doing is we are flattening the surface out on the top to remove all the available features, and we are flattening the top, and over that we are making our own end mill cutting tool, that's like micro end mill tool. Okay, this micro end mill tool, so why we are using a blank of like commercially available tool, that will be easily easily can be put into the spindle, put into the collet, the collets are available, that's the only reason we are using that, and our actual tool will be on the top of that, just like a pencil carving. Okay, as the next step, I will demonstrate the whole setup, whole experimental setup to you, and will demonstrate the machining process. Okay, okay, let's see what is the setup for fabrication of micro end mill tools. Okay, so from here I think you will be seeing there is a spindle, and there is a workpiece which is set up on the bench on the vise. Okay, the both material for the tool blank and the standard piece is tungsten carbide. So what we are doing here, there is a block and there is a tool, the tool blank, and we will be just touching the tool blank first to find out the point, the touching point. That will be done using a contact probe method. After that, to reduce from 0.5 mm to 0.2 mm, 0.5 mm to 0.2 mm, we will be moving 150 micron inwards, and we will be moving along this direction, so that the sparking will be occurring between the tool and this standard piece or the tungsten carbide block, and the dimension will be reducing from 500 micron to 200 micron, because why? It's going inside by 150 micron and it's rotating, so that 300 micron will be taken from the outer vise, and the left, and what will be left, 200 micron diameter. Okay, this is just like a turning process, but there is no tool available, no cutting tool available, or the whole machining is done by the sparks. Okay, then if to get a more fine view, we will be changing the view to the microscopes. Then we will get how the machining happens and how the sparks will be responsible for the machining. Okay. So for a better view, we will be changing the view to the microscopes, because we are dealing with very small dimensions and in micro dimensions. So by naked eye, the process will not be much visible. So the whole process we will see as in the microscopes. So here you can see the micro commercially available 4-flute micro end mill tool, which we are going to use as a blank for our original the micro end mill tool, which we are going to make. And here you can see the flanks and all. What we are going to do is we are flattening out the bottom of it. We are reducing the diameter into 200 micron, and after that we will be doing the plunging and all. Okay. So there are two cameras actually we are using. So one camera is this one, or one microscope camera is this one, and another is so there are two cameras we are using. One is this one and one is attached to the machine. So this is a digital microscope camera and that one is a charge coupled device, CCD microscope. Okay. To explain that, you can see here. So this is a CCD microscope, this is actually the shadow of the whole tool available. So you have seen the original end mill tool which is connected there and which has shown there, and this is actually the shadow image of it. In this actually we can measure the so I am just trying to rotate this one. So now you can see it's, so I will rotate in very slow manner. So okay, this is actually the micro end mill tool which we have shown there. So you can see the flute and all. So why we are using this one? So after making the tool or while doing the manufacturing process, we are not sure the dimensions are correct or not. So if frequently we have to check the dimensions in the microscopes. How to do that? We can actually capture this shadow image. Capture the shadow image, and just like here you can capture it and that will be shown in the figure. So and we can measure the dimensions, that is a measuring system, and we can measure the dimensions, and here you can see the length is showing for around 500 micron which we are originally using it. Okay. And so this is, for this purpose we are using the CCD camera and the software which is connected to it. Okay. So what we have told, like we have using two cameras for measurements and to view what's happening, is it correct or not, the process is correct or not, any problem with the process. Okay. If so, everything is ready, two cameras are ready for the measurement and for observation, and the machine tool is available for it. So before starting the machining, we have to find out the points, the boundaries of machining, like where we have to start the machining. For that we have to use a contact probe method. The contact probe method is nothing but it will find out the point, the touching point, by when the shorting occurs. We will be moving very near to the standard piece or the tungsten carbide block, and as it touches the block, then what happens, that there will be some shorting and that point will be taken as the contact point. So that what we will be doing, just remember, we will be touching and we will be moving 150 micron inwards, and we will be moving in y direction, so like in one other direction, so that the diameter will be reducing. Okay. So next I will explain how to use the contact probe method. So I am changing into MDI mode, so the manual mode, and So, in this you can see from the microscope that the tool is approaching the tungsten carbide block, and once it touches the tungsten carbide block, the program here it stops. Like I have written a skip function program, so that as it touches the tungsten carbide block, this stops, and that point we will taken as the starting point, and we will move inside 150 micron and move alongside, so that it will be machining into the required dimensions. So, this is the point has been set into the contact point has been find out using the contact probe method, and that's set into the 0. Then we have to move 150 micron inwards, and we will be doing the machining. Okay. So, we have to write a program for that, and we will be writing in an auto mode. So, this is very much similar to all the CNC programming methods and CNC programming machines, or all the CNC machines. We will be rotating this clockwise in 2500 RPM, and we are moving X into my 150 micron inwards, and after that we will be moving in Y direction . 5 mm. So, here feed is 0.3 and we are moving 5 mm in Y and 0.15 mm in X, and we are stopping the spindle. That is all about it. So, before starting we have to set up the electrical parameters first. We will be starting the power. We are changing into number 4, and increasing the voltage to 100. Okay. So, here, and we have set the program, we have set the electrical parameters. Now, we have to start the dielectric fluid. The dielectric fluid is very much necessary to perform the operation. So, the fluid is flowing in between, and we are, so everything is set, the discharge, the dielectric fluid is flowing, and the electrical connections are ready. and we are just going to start the machining process. Okay. Now you can see from here, from the microscope, that there is sparking occurring between the blank and the block. So as it goes 150 micron and moving into the y direction, the diameter will be changing from 0.5 mm to 0.2 mm, and we will be reversing the tool down and we will be flunging the fluids on the tool blank. So to explain what happens if I am increasing or changing the machining parameters, I can explain you. If I am changing the electrical power here, so you can see that the discharge energy increasing, or the spark intensity is increasing. So as I am increasing the voltage and capacitance, we can see a very heavy sparks on it, and as I am decreasing the capacitance, the sparks decreases. That what I am told, like if we are increasing the capacitance and voltage, the discharge energy increases, the crater dimensions increases, and the surface roughness will be increasing, the MRR will be increasing, but the surface roughness will be also increasing, like the surface quality will be diminishing. So this will be the process, and but this is a micro EDM or EDM process. In always it's very time taking process compared to the conventional machining processes. So this will take much time for machining, and as a next step we will be showing the machine tool. So the final machine tool which we are going to use as a micro end mill tool. Thank you.